Okay, this is going to be our second video in our inductance series. In this video I'm going to be talking about the content from section 30.2, so self-inductance and inductors. And so let's get right into it here. In the last video we saw that changing current in one coil can induce a current in another nearby coil, right? We're now going to explore a sort of related effect in which a circuit which is carrying a varying current has an EMF induced in it by the variation of its own magnetic field. So we have a current running through our circuit. This is causing a change. Well, we have a changing current running through our circuit. This is causing a changing magnetic flux through the circuit, and this is inducing an EMF in that very circuit. Okay, so self-induced EMFs can occur in any circuit, but the effect is definitely enhanced in circuits where you have like coils with a number of turns, or something that mimics coils with a number of turns. So you have to be careful for that reason, right? For a coil with n turns, carrying a current I and with a magnetic flux given by this symbol here, our phi b, passing through each turn of this coil, we have a self-inductance given by the expression shown below here. So our self-inductance, which we give the symbol L for, is equal to the number of turns in that coil times the magnetic flux going through each of the coils divided by the current in the coil. Okay, and so let me just, I've been having some sound issues here, so I want to double check that I'm actually recording here. It seems that it's working. So we can keep going here. If the current I here changes, so does the flux, right? We know that I and the flux are connected to one another, and if I changes, our magnetic flux changes too. We can rearrange the equation that we have here, take the derivative of both sides, like we can slide I over to this side, then take the derivative of both sides. Our time derivative only bites on the magnetic flux and the current. Those are the only things, two things changing in time here. And so we can write down this expression. Then from Faraday's law, we know that this is true, this first equality. And because of what we just wrote down above, we can write it in a second form like this. Okay, and this is going to be a very useful expression. That's why I boxed it here. This is going to be our self-induced EMF, right? And this is our self-inductance, our L that we just talked about. Okay. Now let's talk about inductors as circuit elements. Okay, so a circuit element that's designed to have a particular inductance is called an inductor. Okay, it's usually given the symbol that we see here, like this green squiggly thing. It doesn't need to be green. Oftentimes you'll see it written in black. It'll kind of just look like this, right? Where a resistor kind of looks like this. They're kind of two different symbols that we would use. Okay. So basically this is a symbol for an inductor, and let's remember, like, why would we use this in a circuit? Well, inductors oppose variations in current through the circuit, right? So let's say for some reason we had a circuit, we wanted to really oppose any change in the current going through the circuit. Well, those would help us do that. Okay, we're now going to develop a general principle that helps us use, well, that allows us to use these inductors in our circuits, or at least allows us to do calculations using Kirchhoff's loop rule in circuits that contain these inductors. Okay, so we want to be able to use Kirchhoff's loop rule and use Kirchhoff's laws to be able to do calculations where these inductors are included, and we need an extra sort of piece of the puzzle here to be able to do that. So I'm not sure why I didn't bother sort of boxing off all of this, but basically you can kind of think of this all as the same box, which extends onto the next page actually. And why I've boxed this off is because what I'm talking about here is sort of a derivation of the final rule that we're going to use to be able to apply Kirchhoff's loop rule to this. This is sort of the punchline of all the stuff I'm going to talk about in this box here. This is the most important takeaway message. Now, what I'm going to talk about here for the next page and a half is important, but if you sort of don't follow it and you're only able to remember one thing from this discussion, I would say definitely remember this. This is the sort of key takeaway message. The rest of this stuff is the derivation of that. Okay, so I'm going to go through the derivation because I still think it's important to see, but the key, most important message is definitely that last equation that I just showed. Okay, so if we want to use Kirchhoff's loop rule on this stuff, we're going to begin by going around a conducting loop. Well, this is what we would normally do when using Kirchhoff's loop rule. We're going to go around a conducting loop, measuring the potential difference across successive current elements, right? So we're going to go around, we go over a resistor, we measure the potential difference across that. We go across a battery, same idea, depending on our directions. We're adding or subtracting these terms, and so we go around the loop, and if we go around the loop, because our circuit is a loop, we know that all of our potential jumps need to add up to be 0 when we go around the full loop, right? And this is because the field produced by the charge around the loop is conservative, and we give that conservative electric field around the loop this symbol here. Okay, electric field subscript C, so it's electric field conservative. Okay. When we include the inductor in this loop, let's say we have a loop, we then plug a inductor into the loop, the situation changes a little bit. Okay, the magnetically induced electric field within the coils is not conservative. We talked about this before, right? So we have this not conservative electric field, which we give this symbol, so electric field non-conservative. And so we now have this conservative electric field and this non-conservative electric field. Okay, so let's take a look at sort of how we're going to handle this situation. Let's suppose, and I'm sort of starting off from here, let's suppose that we have an inductor whose coils have negligible resistance. Okay, so we have an inductor with very little resistance, or basically no resistance. Well, imagine the situation, the limit. We've already talked about superconductors. What happens if we have a current running through a superconductor and we turn off our electric field that's driving that current? Well, the current continues to flow, right? So in this case, let's say we have very little current, or very little resistance, I should say, in our coil. Well, this is somewhat analogous to the very low resistance or next to no resistance of our superconductor, right? So if we have no resistance, well then it must mean that we need a very small electric field to drive the current through the coil, right? So that must mean that the total electric field, our conservative electric field plus our non-conservative electric field within the coil, is basically 0. Okay? And this is true even though neither of those fields, neither our conservative electric field or our non-conservative electric field, are 0. Okay? Individually they're both non-zero, but when we add them up, they are 0. Okay? But then because this conservative electric field is not equal to 0, there must be an accumulation of charge on the terminals of this inductor to produce this electric field, right? So let's get a picture sort of involved here so we can think about this. We can imagine this loop here. We can imagine we're going around where there could be other stuff here, but for this case we're only looking at our inductor with self-inductance L sitting in the loop here. And so we can imagine we're going around it, and there's going to have to be some charge building up so that we have some non-zero conservative electric field across this thing. And so then what does Faraday's law tell us? Faraday's law tells us that the line integral of the non-conservative electric field here around the loop has to be given by this expression here, right? That's what Faraday's law tells us. Okay? And then from equation 2 from above, so from this equation here, we can rewrite part of that Faraday's law for our non-conservative electric field. We can rewrite this term in these terms. Okay? Then when we integrate around the loop, okay, so we're integrating around the loop following this loop integral. This is a closed loop integral, so we need to integrate around the whole loop. But we're only going to pick up contribution from A to B, right? There is no non-conservative electric field anywhere except inside our inductor, right? And so because that's the fact, we can replace the full loop integral with just an integral from A to B, right? Because we're not picking up contribution around this part, we only get contribution between A and B. So we replace the loop integral here, the full loop with just the integral from a to b. Okay, and then because we discussed before how our conservative electric field plus our non-conservative electric field has to be equal to 0 in that region, well, it must mean that our non-conservative electric field is equal to the negative of our conservative electric field. So we can just plop in minus EC here for En, cancel out the minus signs, and we end up with this expression here. Okay? But this integral on this side here, this is just the potential difference across, well, from a to b, right? This is just VAB. So we can just replace this integral with VAB, and now we have a nice tidy expression, which I have boxed down here, that gives us an expression for the potential difference across AB, across our inductor, written in terms of the self-inductance times the time rate of change of our current going through that inductor. Okay, and now with this expression, we can again go back to Kirchhoff's loop rule, right? We can now use these inductors and make calculations using Kirchhoff's loop rule, because we know what the potential difference across this thing is going to be. It's going to depend on L, our self-inductance, and how quickly the current is changing going across that inductor, right? So let's remember really quickly here, and make a note again to remember that the self-induced EMF resists the changes in current flow. Okay, so it resists di dt. It wants to make di dt 0, right? It doesn't resist current flow itself, right? So as much current as you want can flow through an inductor, and nothing's going to happen. It's only when you're changing that current that you're going to have the inductor start resisting the change in that current flow. Okay, and so this figure here does a nice job of sort of demonstrating the difference between a resistor, the way a resistor acts when it has current going across it, and the way inductors act depending on the sign of your derivative, right? So depending on whether you have no derivative, or your derivative is equal to 0, or whether you have a positive or negative di dt, right? Assuming these are all the same L. Okay. So we will come back to look at these in a minute as we're doing some examples, but let's get into 2 examples here. And yeah, okay, so I'll mention it as we get to it, but we'll start off with this example. So this is 30.3 from the textbook. We're calculating the self-inductance of this toroidal solenoid. Okay, so we want to so maybe first look at the picture here. What do we have going on? Well, we have kind of like a solenoid is usually like sort of a cylindrical thing with a coiled wire around it. Now imagine that we kind of bend this thing around on itself and we turn it into a torus, right? We turn it into this toroidal donut shape that you see here with wire coiled around it. This is a very common configuration for this type of setup, right? So there was an example in chapter 28. It was in section 28.7, where we were looking at applications of Ampere's law. There was an example at the bottom of that section. I think it was example 28.10, where they do the calculation of the magnetic field inside one of these toroidal solenoids. I purposely skipped that because I thought that was a very good example that people could go back to and actually sort of do it on their own, but not completely on their own. They still have the sort of support of the textbook giving them the answer and going through step by step how to get it. But again, let me recommend that's a very good example to sort of go through and take a look at, and maybe something that would be useful, for the assignment or for the final or something. So we are going to use that result, so I'm going to sort of quote that result without deriving it here. But if you want to see how it's derived, and if you want to do a good example that has a lot of interesting sort of ins and outs, a lot of interesting sort of steps in the calculation that are applicable to other problems, I would take a look at 28.10, which is done in detail in the textbook. Okay. So having said that, let's get back to this problem. So we want to determine the self-inductance of a toroidal solenoid with a cross-section A. So this is like the cross-sectional area here on the diagram, with a radius R. The radius is for the whole solenoid here. Okay. closely wound with N turns wire and a non-magnetic core. Okay, so we have a non-magnetic core, we have wire tightly wound around this, we have N total windings, and the setup is as you see here. Okay, we're going to assume that B is uniform across a cross section here. Okay, so B is uniform wherever we have B. We're just going to assume that it's a uniform B, so we don't have to worry about sort of integrating over it. Okay, and it's going to be uniform sort of in this direction, right? I mean, uniform in all directions, but we're not going to worry about sort of variations, small variations at the edges. Okay. So let's sort of get into it. We want to find L, right? So we want to know what is L, our self-inductance. Well, 30.6 gives us that L is equal to the number of turns in our coil times the magnetic flux through each one of those turns divided by the current going through the wire, right? And so to get this magnetic flux, we would need to go and do that example. Okay, but I'm just going to give us the answer here. We can go back and certainly look at that, but we want so we're going to kind of step up to this. To be able to get this, we first need B. We need the magnetic field inside this solenoid, inside this toroidal solenoid. That's the value we would have calculated in 28.10. And if we do that calculation, we find mu naught Ni over 2 pi r, where these variables here are exactly the variables that we've labeled above. Okay, and I is what we're now calling lowercase I because it's varying in time. Okay, so this is sort of an intermediate result that we would have gotten from 28.10. That's the example, 28.10. Okay, or I should probably write, and it's also in 28.7. That's section 28.7. Okay, so if we have that result, then we're really most of the way there, right? Because we know that the magnetic flux is going to be equal to the magnetic field times the area, right? So we can just rewrite this and jam in the area. We're going to end up with mu naught Ni times the area over 2 pi r. Okay? And then, well, we know, now that we have our magnetic flux, we know what L is in terms of magnetic flux. We can easily write that. We can write that L is simply, well, I'll rewrite it one more time, and then just substitute in for our magnetic flux. So this is just going to be N mu naught N Ia over 2 pi r I. Okay, these i's will cancel. We can collect up these n's, and so we're going to end up with an L that's equal to mu naught N squared A over 2 pi r, like that. Okay. Something like that. So that's the sort of result that we're looking for here. That's L in terms of quantities that we could measure for our toroidal solenoid. But we're going to put some numbers to this because, like in the previous section, we're going to carry this forward and do something with this in the next example. So let's say we have an N. Okay, so suppose we have an N equal to 200, so we have 200 turns around our toroidal solenoid. Let's say we have a cross-sectional area. Remember, our cross-sectional area here is this. Say we have a cross-sectional area equal to 5 square centimeters, but we're going to write that in terms of square meters, so that's going to be 5 times 10 to the minus 4 meters squared. And let's say we have a radius, so that's the radius of the whole toroidal shape here, and that is going to be a radius equal to 0.1 meters. Okay, if we plug those numbers in, we're going to get an L, a self-inductance. Again, in terms of henries, we're going to write it in terms of microhenries. So we're going to have 40 microhenries. Okay, so that is our self-inductance, and we're going to use this value in this next example. Okay. So let's say we are, well, okay, so this is example 30.4 from the text. It's the last example in this section. We're going to be calculating the self-induced EMF. So let's say that we are looking at this problem. We have the current in the toroidal solenoid in the example we just did above increasing from 0 to 6 amps, right? So we have I, it's going from 0 to 6 amps, and it's doing this in a time equal to 0, or maybe I should just do it like this, 3 times 10 to the minus 6 seconds. Okay. So what is this changing I really telling us? Well, this basically gives us, because it's doing this uniformly, we know it's true at every point along this time interval. So what it's really telling us is that di dt, the timed rate of change of our current, is actually going to be equal to 6 over 3 times 10 to the minus 6. That's supposed to be a 10. 3 times 10 to the minus 6 at every point where this current is increasing. Okay, so if we do that calculation, we can see that di dt is really equal to 2 times 10 to the 6 amps per second. Okay, so that'll be useful to know. And why is that useful to know? Well, if we use equation 30.7 from above, okay, we use equation 30.7 from above, which I won't scroll up to here, but 30.7 tells us that our self-induced EMF is going to be equal to minus L di dt. Well, we know L, we just calculated that in the previous problem. We just got di dt, so we can stick those together. We're only going to be interested in the magnitude of our EMF. We're going to use, we could use lens, like Lenz's law, to determine the direction of this thing, so I'll talk about that briefly in a second. But just to get the magnitude, if we just want the magnitude, we can just write it down like this, L di dt, and we can simply calculate it. That'll be, what did we get before? We got 40, we got microhenry, so it's going to be 10 to the minus 6, and then here we got 2 times 10 to the 6, and so we find the magnitude of our self-induced EMF is going to be 80 volts. Okay, so that's the magnitude of the EMF induced in our toroidal loop here. And if we want the direction for this self-induced EMF, well, we can see that di dt here is positive. This is greater than 0. Okay, and this means that our self-induced EMF here is going to oppose. Oh, that was terrible handwriting. Sorry. It's going to oppose I. How do we know that? Well, we can see that from the diagram that we have above here, right? We can see that in the case where our L di dt is greater than 0, that's the case that we have here. If we have current flowing in this direction and increasing in this direction, like our di dt is greater than 0, well, then we're going to have an EMF working in the opposite direction. Okay, so where we have current flowing from A to B, we have EMF pointing in the direction from B back to A. Okay, and so that'll wrap it up for this section. I'm going to leave it here for this one, and I will see you guys in the next video.